Hey, welcome to Lesson 7. We're still in Module 1, and today we're talking about mid-latitude cyclones. We're going to start with air masses, then we'll move to fronts, and then we'll build the cyclone. So the air mass is an immense body of air. It's usually 1,600 kilometers thick, just like really wide, not very tall, just really wide. And it's characterized by homogeneous physical properties. In particular, we're talking about temperature and moisture being the same throughout at any given altitude. I give you a picture of a desert because the source regions, the place where these things come from, need to be areas that are physically uniform and relatively stagnant. So desert is a place that's perfect for that. So that is the source region. It is a large area where the air masses originate. That's where they're born, so to speak. And like I said, it has to be extensive and physically uniform. So the area is usually characterized by general stagnation of atmospheric circulation, meaning it doesn't move. And usually that means that there's high pressure with diverging winds. So polar regions are particularly effective for this because of additional radiational cooling. This is what radiational cooling looks like. Starting from the less to the more end of the potential for radiational cooling. So if on the less end we have, let's say it's nighttime and there's some clouds. So the clouds actually act as a blanket and will block the heat release from happening. So it kind of re-radiates downward and keeps it warmer at night. Wind also does the same thing. Remember when we talked about freezing temperatures in orchards, they use wind, mills, and turbines to kind of keep that from happening. So that will also keep it from being too cold. If I have clear skies and calm winds, that would be ideal for this kind of cooling. And then if there's snow cover, it will allow for even more rapid heat loss. So we classify air masses with a lettering system. So the first letter is going to be lowercase, and that describes its latitude or its temperature. And then the surface area is going to be a capital letter, and I'm going to go through each of them. So for latitude, I'm sorry, I mixed this up. They're actually backwards. Anyway, let's go through it. So latitude, there are three different ones. One is Arctic, one is polar, and one is tropical. For Arctic, it's capital A, polar, it's capital P, and tropical is capital T. So there's one out of three categories. Then there's two surface areas. One is little m, which is maritime or marine. Sometimes I say marine, that's why I put that in there. And maritime is how it's referred to in the textbook. Then continental is a little case, lowercase c. So then we put them together. So you might be saying, okay, professor, so if there were 3 latitudes and 2 types of surfaces, that should be 6, right? So why are there 5? Well, at this point in time, there is no Maritime Arctic, and that's because the North Pole is covered by ice, right? Sea ice. So the sea ice acts kind of like a surface of land, and therefore we have Continental Arctic instead of Maritime Arctic. So there's no water up there exposed, at least so far. So anyway, let's move forward. So we have Continental Arctic, that's lowercase c, capital A, which is very cold and very dry. It is the coldest on the planet. Then we have lowercase c, capital P, which is Continental Polar. This is cold and dry, so it's a little bit warmer than the other one. Then we have Continental Tropical. This is the hottest, so this is hot and dry. So these are associated with deserts. And then Maritime Polar is little m, big P. This is cold and wet. And then Maritime Tropical is warm and wet. So it's little m, big T. So we get something called air mass weather associated with these. This is when some region is going to experience the same kind of consistent weather because the air mass is traveling over that area. So we see here one of the Arctic air masses was dislodged. We have cold, dry air mass, negative 46 degrees Celsius. It's dislodged and moved southward. So we see all the way in Tampico, it's 10 degrees C, which is quite chilly for that area. That's in Mexico, by the way. And then I show you this video in class. It's boiling water. So it's boiled, and then he throws it outside in negative 41 degrees C, and you see how it changes. I'm not going to spoil the video, but it's awesome. You should definitely see that. Okay, so we're going to start with the winter, and then we'll move to the summer and what happens to our different air masses. In the winter, we have Continental Polar and Continental Arctic. The Continental Arctic is very cold and very dry. It is the most extreme air mass. It forms near the poles and delivers record cold temperatures if it dislodges and moves somewhere else. It produces epic lake effect snow. So there's like lake effect snow, and then there's epic lake effect snow. These are measured in yards, okay, instead of feet. So yes, 3 feet in a yard, just, yeah. Anyway, all right, outside of that is the Continental Polar. Little c, big P. This is cold and dry. Also stable, it delivers relatively chilly conditions and produces lake effect snow, which I'll show you in a second. So these two live up here. If they spread, that's when that cold is extended to the other areas. Here's lake effect snow. So this is colder air over warm water. This phenomenon mainly occurs in the autumn and early winter. So at the time of this recording, we're going right into that season. So step one, we have the CP air mass moving over open water right here. And the Great Lakes are relatively warmer in the winter time. We see it's 1 degree C. I know that sounds chilly, but the surface temperature is negative 18 degrees C. So that's almost a difference of 20 degrees C. So it moves over the warmer water. Moisture is added to the air. The temperature increases a little teeny bit. Then it moves over the land over here, cools rapidly, and it drops out lots of moisture as snow. So this is kind of what they look like. There's a snow squall right there, and you end up being buried as such. That's a car with lots of snow on top, and you see these kind of canyons, right? So they have to like make tunnels to get out of their house. Wah! All right. Now, around the world, do we get different air masses? Yes. So occasionally we'll get this strong, cold, dry, stable, under high pressure over Siberia. And if it moves southward, it actually will pick up moisture from the Pacific Ocean. As it does that, it modifies the air mass to the point where when it comes to the west coast of the United States, it's actually an MP by the time it gets there, so Maritime Polar. This is now cool and moist. It's not as cold as it was here because the ocean water has influenced it. So when this reaches the west coast, it's usually accompanied by low clouds and shower activity. So we see these can move all around the globe. All right, so the next one in winter, since we just talked about it, the Maritime Polar. This is warmer than a CPC air mass. It's from the Pacific that we experience most often. More so than the Atlantic. This one's only pulled in when we have nor'easters. And we'll get to that later. So these are unstable because they have more moisture associated with them. And there's low clouds, fog. Most of the time it's pretty clear. There's also onshore winds. They can be precip free, but you might get drizzle depending on the other conditions. Moving forward, we now have Maritime Tropicals, so we see that out here. Notice that for the most part in the wintertime, the Continental Polar is the ruling kingdom, right? It's the army that's kind of taken over. And then out here in the Atlantic, we see the Maritime Tropical. It's warm and humid. Most of the time, we will be influenced by the one from the Atlantic and the Gulf of Mexico. It is unstable, and over cold, snow-covered surfaces, it leads to thick fog. And actually, when this one starts to move on shore, which you'll see in the summer slides, it leads to that thawing of winter conditions. So it flips our seasons. And this one we don't really get influenced by. There's kind of special scenarios for that, which we'll get to in the El Nino chapter. Okay, so now we flip to summer. You notice immediately that the Continental Arctic is gone. Thank goodness. Goodbye, I don't want to see you anymore. So the Continental Polar kind of retreats northward. You see it's not as far south, so it retreats northward. And now it's considered cool and dry. It's also still stable. It offers kind of a break in the heat and humidity during the summer. forms over central and northern Canada, and it sweeps southward. Winds from the northwest, it's dry, very little precipitation because of the dryness, usually partly cloudy skies. Then a Maritime Polar, notice those also moved a little bit northward. These are warmer than the CPCA. It's unstable. We have cool conditions to the shoreline areas, but again, usually precip free. And then finally the Maritime Tropical. Oh, I'm sorry, there's one more after this. So the Maritime Tropical, little m, big T, is warm and moist. It's unstable. We have steamy weather. This is where you get like that Velcro sticky. That's what my boss used to call it, Velcro sticky conditions. Very, very uncomfortable. Any kind of lifting can release torrents of rain. A lot of moisture associated with this. Dew points above 70 degrees Fahrenheit. Heavy thunderstorms, also famously associated with the Bermuda High. All right, now the last one. So the last one is Continental Tropical. This one was not present during the winter. It's only present during the summer. So this is an extremely hot, dry, and stable at the surface, but unstable aloft situation. It develops over deserts, like I said. Skies are usually clear. It causes a persistent high pressure to form, which if that happens during the spring, it's a very bad sign for the summer. It can also set up what's called a dry line, which we'll see a little bit later, which is an abrupt change in moisture between the CT and the MT air masses, which makes for good storm chasing. Yay! All right, the last one I just want to kind of put out there just for fun is the rare beast, as I call it, which is the Equatorial Air Mass, or the E. This is extremely warm and humid. Like you can't even fathom how warm it is. It's like a Maritime Tropical on steroids, and dew points can reach above 80 degrees Fahrenheit. I've only experienced this one time, and it is miserable, like so uncomfortable. So hopefully we don't see too many of these. All right. So what about that North Pacific Maritime Tropical Air Mass? Well, it's not really known for its impact on North American weather because of the upper level winds. Now, it can cause a phenomenon known as the Pineapple Express, not the movie, and it comes from Hawaii and then moves from Hawaii into Southern California. It sets up what's called an atmospheric river, and it brings extraordinary rainfall to Southern California and the other West Coast locations. So when it moves northward, this air mass will actually cool and cause low layers to become more stable, which makes fog and drizzle and moderate precipitation. So there is some flooding, yikes, associated with this type of setup. So I asked you in class, what's the air mass outside today? And when I'm recording this, it's pretty dreary and chilly. I actually think we have a backdoor cold front, so it could be a Maritime Polar, actually. All right, so let's talk about backdoor cold fronts. What are fronts, Professor? Good question. So a front is a boundary between two different air masses. This whole process is caused by overrunning. So the warm air has to glide up over the cold air because the cold air is more dense. So it gives way for the warm air to move up over top of it. So as soon as the front passes some particular location, the weather can change from steamy maritime tropical air to dry, cold continental polar. These contrasts lead to stormy conditions, stormy weather developing, and fronts are named by the type of air that is overtaking the other air. So if cold air is advancing, it's called a cold front. If warm air is advancing, it's called a warm front. That's how that works. So here's a total cyclone. We'll get to building this in just a few minutes. So we see an occluded front, which is purple, cold front, which is blue, warm front, which is red, and then, yep, that's all of them. Oh, stationary front over here, which is both, and a three-dimensional cross-section from A to B. I see cold air mass behind the cold front. That's the one advancing, so it's called a cold front. Warm air mass here, cooler air mass there. So the warm air is advancing. It's a warm front. Okay, so what are cold fronts? Cold fronts are zones of discontinuity when cold air actively advances into a region occupied by warmer air. So where there's a continental polar air mass or a maritime polar air mass, it pushes aside the tropical air mass. So temperatures might not always drop, but your dew point always will. So this is represented on a map with a blue line, blue triangles pointing in the direction of travel. There's slopes here. It's about twice as steep as a warm front, so it leads to violent conditions like thunderstorms and tornadoes. So there's not much warning ahead of it. You just see like a very skinny line of storms and then it's gone. So that backdoor cold front I was just talking about, this is when instead of moving from west to east, which is normal, it becomes east to west. So this is in the northeast United States. We have this lovely little situation. Usually happens in the spring. So the warm weather goes away and we get cool and moist conditions. So it might be 70 degrees, sunny, and then this backdoor cold front comes from Greenland. It's pushed onto shore. So this is all the MP air being pushed on shore. So we get 50s, rainy maybe, nasty, right? Okay, warm fronts. This is when, I'm going to move me, here we go. When the surface position of a front moves so that the warmer air is invading the new territory that was formerly occupied by the cool air. It leads the way of the tropical air mass. It's shown on the map with a red line, red semicircles pointing in the direction of travel, and they have relatively gentle slopes. So you can actually see the cloud deck lower as this front gets closer to you. So we'll see cirrus clouds, then cirrostratus, then altostratus, and then nimbostratus. That's when it starts raining. So if you start seeing cirrus and then cirrostratus and it starts to lower, you can say to your friends, oh, it's going to rain in like the next 12 to 24 hours, and you'll probably be right. And then you can impress your friends, which is great. Now, that's unstable air. If I have unstable air, you can actually kick off some thunderstorms, and you can definitely get icing and freezing rain during the winter time. So this was, oh, that's perfect. This is what they look like before, during, and after passage. So for my cold front, starting over here, temperatures should be warmer before, dropping during, and then colder after. My precipitation should be a little narrow, only during passage, not before or after. Clouds should be, again, none before, cumulonimbus maybe during passage, and then none after. Then the pressure should be falling. During passage, it starts to rise. After passage, it should rise because now my low pressure is gone because the cold front is the last to go, and then it should be replaced by high pressure. In the summertime, my humidity should be higher, then it should drop, and then I should have lower humidity after passage of the cold front. Moving to my warm front, I see cool or cold conditions before, then my temperature should start to rise. It should be warmer after passage because warm air is taking over, right? And my wind should move from the southeast to variable during passage to south. And precipitation will be before passage, not like the cold front. So before passage, I'll get all my light to moderate rain, snow, freezing rain, whatever. Okay, you can get heavy rain in the summertime, none during passage, and then none after passage, unless it's the summer, and then you might get some showers. Before passage, when you have the lowering cloud deck, which we covered, cumulonimbus can be happening if it's conditionally unstable, then none or fog, and then after it should be clear. Then pressure should be falling, 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 and then afterwards it should be falling, right? So it should be falling because I'm going into the center of the low when the warm front passes. And then humidity should be moderate to high before, and then it should rise and be really high, especially during the summer, because I'm bringing in a more moist air mass, so it should increase my humidity. So if you need this as a reference, these are in the textbook. Again, the weather associated with your cold and warm fronts. Then we have something called an occluded front. So an occluded front is a merged front. It's when the cold front overtakes the warm front, and so it can't get out of the way fast enough. Cold front overtakes it. It shoves up the warm air, so we get this new front at the surface called the occluded front. Now, you can get it the other way around, down here, where the warm front does the overtaking of the cold front and then the cold front moves, That is called a warm type occlusion. I'm just mentioning it. Happens mostly in the Pacific Northwest, but we don't really cover it in this class. We're going to talk about cold type occlusions because that's what we see mostly. So it's represented by a purple line with alternating semicircles and triangles in the direction of movement. Here's what it looks like totally together. So we see a mature mid-latitude cyclone. We're about to talk about that. We see a low pressure. It has like these arms or legs. Those are its fronts. So we have a warm front here, cold front here. If I take a slice through and get a cross section, I see my cold air is advancing very quickly. The warm front, not as much, right? There's our clouds. We have a warm air sector here. Then as it occludes, the cold front takes over the warm front. So then we see that occlusion here, which is happened to be that little point, right? So the occlusion is that little point right there. So the heavy rain is lifted, and then as the cold air continues to advance, right here we see it kind of like a zipper effect, and the warm front is completely eaten alive, and we get this occlusion. So once this happens, it's pretty much the end of the cyclone. So it's going to lose all of its strength because it cut off its warm air. That's what it needs to survive. All right, so we also have these things called stationary fronts, literally meaning that it doesn't move, and so or it doesn't move or it's moving sluggishly. So it's indicated by red semicircles and blue triangles alternating sides, and they may remain over an area for a long period of time. Yikes. So that means lots of precipitation, which can lead to flooding and other such things. So, okay, dry lines. So I talked about this a little bit ago. This is when we have a dry, warm air mass. Over here, there's our CT air mass, and then a warm and more humid air mass over here, and then it produces this kind of boundary, and this boundary is called a dry line. So you see my dew points over here in the 80s, dew points in the CT air mass are in the 50s. So that abrupt change of almost 30 degrees is what causes this dry line to happen. And they most often generate thunderstorms, pretty good ones actually, which is why these little squiggles are here that are supposed to be tornadoes. I think they look like question marks, but whatever. It was in the textbook. Okay, so I asked in class, which front do you think can cause the most dramatic changes in weather? And it's kind of subjective, right? But usually I'd land with probably a cold front or that dry line that we just talked about. Okay, so mid-latitude cyclones. What happens with all these different air masses and fronts, right? So the atmosphere actually has a lot of energy that's waiting to be released. We call that potential energy. A little bit of physics here. So the specific areas where that temperature contrast exists is said to have available potential energy, or a baroclinic zone. So a mid-latitude cyclone is a large low-pressure center with a diameter often exceeding 1,000 kilometers that moves from west to east and may last from a few days to more than a week, and usually has a cold front and a warm front extending from the center of the low pressure, and they frequently produce precipitation. So who came up with this? Well, it comes from the Norwegian cyclone model, and it's called polar front theory. It was a theory developed by Johannes Bjerknes, that's fun to say, right? And other Scandinavian scientists, meteorologists. They came up with this idea that the polar front, which separates polar air from tropical air masses, gives rise to these cyclonic disturbances that intensify and move along the front. They pass through a succession of stages, which we're about to go through, and develop into these cyclonic systems. So they develop with the polar front. It's usually during the colder months that this happens. Well-defined bands around the Earth during the colder months. The frontal zone is broken into distinct segments at the surface where our cold air collides with our warm air. Okay, so step one, we have something called cyclogenesis. This is the birth of our storm. So this is development and strengthening of the storm system. So part A we see here, it looks kind of like a stationary front, right? and it forms where the air masses of different temperatures and densities move parallel to the polar front but in opposite directions. Next, under the right circumstances, that boundary will become wave-shaped. So we see here, whoop, it's got a wiggle in it. So that would be the wave shape. As the storm intensifies, the wave also changes shape. So part C, here we are. The warm air is now advanced poleward, because that's the opposite of where it came from, right? And then the cold air moves equatorially, forms a cold front. Sorry, the first one forms a warm front, the other one forms a cold front. The low pressure is in the crest of the wave, right there, and the air begins a counterclockwise circulation. This is what it looks like when it's mature. So we have a simplified surface weather map here. I see a warm front, a little bit of precipitation here. Cold front, notice all of it is ahead of the cold front. We're just along it, right? We see warm air mass here, 70s, juicy air, 66, dew points. Then out here, cooler air, still pretty high relative humidity though. That would be our Maritime Polar. And then back here is Continental Polar. We see 20 degrees and then low dew points, low dew points, low dew points, right? And then rain shield, low pressure in the center. Okay, so that's the mature stage. That's what it looks like. And the pressure around the low is dropping. So our winds are strengthening. More air is moving into the area because it's being lifted, right? Sorry. So frontal weather then develops, so we get that rain shield, we get our clouds and everything like that. Oops, now we have an occlusion, right? So this beginning of the end of the storm, the cold air is now overtaken the other warm front, and the occluded front has begun. So after that, the cyclone is going to dissipate because the warm air is kind of stacked on top of the cold air. It's cut off from the surface. It doesn't have any more energy. So the storm will dissipate. Basically, the pressure gradient has weakened to almost nothing. Okay. Cloud patterns associated with our mid-latitude cyclones look kind of like a comma or an apostrophe, I guess. So we have a comma head here, then we have this tail, and we get this dry slot, which we're going to cover in just a minute. Here's what it looks like from space. So we see that comma tail comes from the cold front, and then the comma head is the clouds wrapping around into the center of the low pressure. So if I take a slice through the occluded portion of the storm, I see all the warm air has been lifted. So none of it is reaching the surface, all cold air at the bottom. And through the warm sector of the storm, I see here's the cold air. There's my cumulonimbus, right? Cold front weather. Here's the warm air in the middle, and then there's my warm front out here. So there can be special mid-latitude cyclones. These are called nor'easters or southwesters, depending on where you are. And these are associated with high winds, heavy precipitation, locally severe thunderstorms, and tornadoes. Also known as snowicanes, because they have really high winds and you can get blizzards and stuff. So snow hurricane, I don't know. It hasn't caught on yet. You get intense, several days of heavy rain or snow along with northeast winds. So if you're west of the center, you get northeast winds. If you're east of the center, you get southwest winds. 1993 storm right here I have pictured, also known as the storm of the century. You know. And these are pretty common between October and April. So they follow things called the jet stream. These are fast streams of air embedded in the westerlies, which we'll learn about later. And these are varying in widths from less than 60 miles to more than 300 miles across, and their speeds reach up to 300 miles per hour. So they're relatively strong. Little ribbon, it's like a metro system through the air, and it is about 10 miles above the ground. So usually we go to this website, and I show you today's. So we go to flight level 300, and we see what the jet stream currently looks like. So Here we have the polar jet stream. So the polar jet stream is to the north. And this actually occurs along that polar front that we talked about before. Jet stream moves stronger in the winter because of that greater temperature contrast. I'm so sorry. Between the poles and the equator. So in the winter, sometimes it moves north to south, which gives us big cold outbreaks. Really cold. In the summertime, it kind of tends to stay to the north. So you can think of this as like the fence of where cold air is allowed to go. So if the jet stream goes south, here comes the cold air. All right, subtropical jet stream is a semi-permanent jet stream, meaning it's there sometimes it's not. And it moves west to east as well, centered at 25 degrees north and south. So there's one in the northern hemisphere, one in the southern hemisphere. And it's slower than the polar jet stream. Okay, and the reason this is important is because it acts as, like I said, a metro system for our mid-latitude cyclones. So they tend to form downstream of an upper level trough. So if I have an upper level trough like this in the jet stream, then that's going to intensify my surface storm. So that's good for the surface storm. That's why they tend to form there. So if I have a trough here, and it's in something called meridional flow, it means it has that big north to south component. It makes my storm move slower so it can develop further. Unlike zonal flow, which is pretty quick, so we can have like one storm after another storm after another storm, which means we won't have as much cyclonic activity because, or at least not as much development because it doesn't have time. It's just zooming along, zooming along. Okay, so air, as you know, goes counterclockwise and inwards into our cyclone, which is convergence. So it spirals inwards and upwards, like I said before, like a Dyson vacuum cleaner. Not a sponsor. And then if it reaches divergence aloft in the jet stream, in this position specifically, this divergence is pulling air out at the top, which means the bottom is losing air, so the air is being sucked up like this and then thrown out. Sucked up, thrown out. So then my surface low actually increases in strength and intensity because of that divergence. And the same is true for the high pressure. If I have convergence here, it's then being shoved downwards, so I'm shoving it downwards and then squishing into the ground, flying out in a clockwise direction that's going to be intensifying your high pressure. So, I asked you in class, how does the jet stream affect air travel from San Francisco to New York? Well, if I'm coming from the West Coast, and I'm going to the East Coast, I can just ride in the jet stream. You can actually arrive up to an hour earlier than the forecasted time by the airline. I know because it happened to me. So that's called a tailwind. It helps the plane. That's why there's a green arrow. So it helps the plane, and it's like the little expressway. But if I'm flying from New York or the East Coast to the West Coast, San Francisco, then you have something called a headwind. So it's like it's pushing against me. I'm trying to go forward, but it's pushing against me. So that works against our plane. You use more gas. So what planes do is they go up above the jet stream, and we fly above it so that we don't have as much headwind. Gee, that makes sense, right? Okay, so where do these things form? They form in these locations. So these are all because of the Rockies, gives it a little spin up, like I said. So we have Alberta Low, it's in Canada, Colorado, in case you were wondering, Colorado, and then the Panhandle Low. Pacific Low is what we get the very most. You'll see that in just a second. Hatteras Low and Gulf Low are good for snowstorms, yay! Especially this one though. Lots of extra moisture to give us our snow. So the patterns of movement move easterly across the North American continent. Again, that North Pacific just comes straight across. We get lots of those. Panhandle Hook is kind of an exception. So it makes kind of like a nice Nike swoosh, sort of. Not a sponsor either. And Alberta Clippers dive down and then across. So it'll get a little bit of moisture from the Great Lakes and then dump it on us. I say dump, more like sprinkle. It's only like 2 or 3 inches at the most. Dumping. It's more like sprinkling. Okay. And then the famous nor'easters. So they come from down here with the Gulf flow, up the coast, gathering moisture, and then that one dumps out as snow. So the modern day view, I'm going to put me over here, of cyclogenesis consists of 3 airstreams. 2 originate near the surface, and 1 is from the upper troposphere. So we'll go through these one at a time. First one is red. Red one is the warm conveyor belt. It starts in the Gulf of Mexico, carries warm, moist air up from the empty air mass into the storm. So we see down here, gathers it up, goes up, over the warm front, over the cold air over here. The next one is the cold conveyor belt. It starts at the surface, goes under the warm air because it's more dense, up and wraps around the center of the storm. Third one is the dry conveyor belt. It's yellow in the diagram, not in real life, and it's relatively cold and dry, so one branch descends. It ends up producing these clear conditions, which is that dry slot that I showed you earlier that comes from the dry conveyor belt, and the other branch maintains this westerly flow into the center of the storm. Ta-da! So that's why we have a calm ahead. All right, some other notable weather that you can get is a blocking high. This is kind of opposite of a mid-latitude cyclone. So blocking high, really strong high pressure anticyclone that blocks or redirects migration of our mid-latitude cyclones for days or weeks. So it just sits there. This one parked itself over the middle of the United States, and all the lows have to travel around it because it's really, really strong. It's like, 1052 millibars. That's really strong for high pressure. This can cause severe drought. This might be what it looks like underneath. We got clear skies because there's no lifting, right? High pressure is squishing everything down. On the other end, you can get little things cut off from the jet stream. The normal flows from west to east. This one has been cut off, so it's called a cutoff low. It remains over the same area and produces large amounts of precipitation for days. Nothing wrong with that, right? Nothing bad could possibly happen. So they might get like feet of snow here because of this cutoff low. All right, a little case study really quickly. This is the storm of the century. So we have, or maybe it's not. Anyway, March 21st, this cyclone reached the west coast over here. Then it rejuvenates east of the Rocky Mountains and moves eastward, there we go, into the plains. So this is where it's been, that's where it's going. So here it is right here. By March 23rd, it's at the Kansas-Nebraska border, and it has a central pressure of 985, which is nothing to sneeze at. It's pretty strong. It has a well-developed cyclonic circulation. It has a warm front and a cold front. That's what it looks like from space. Not super organized. So as we move forward, the next day, the air pressure is deepened to 982, so we know that it's strengthened. The storm is intensified because the pressure has gone down. Storm is curved northward towards Iowa, so it went up this way, and an occluded front has appeared. Aha! So the cold front overtook the warm front. We have an occlusion. Severe weather was produced. Look at this perfect calm ahead. Oh my gosh. So perfect. Just like amazing. All right. So then the next day, the pressure moves up to 1,000 millibars. So we know that occluded front has taken over, so the storm is going to dissipate. The storm is situated over the Great Lakes. It's over here under my face, and it dissipated 24 hours later. This is what it looked like in Iowa. You see lots of snow, blizzard conditions, and that kind of explains what happened. Look at the dry slot. It just completely took over the storm. So no moisture, no storm. All right, those are your vocabulary words. And then in class, what we did is we made little station plots based on this data. Then we drew isobars. Yes, we did. And then we labeled high pressure and low pressures. We labeled the air masses. We shaded in precipitation, the different types, and then we made a forecast for DC, which again is under my face. So if you want to practice that at home, that would be great. It's also in your textbook. I think it's in your textbook. It used to be in your textbook. Hopefully it still is. Anyway, so I hope you enjoyed class, and I will see you next time. Bye.